putting together this school. So what I will talk about in the first 1 and 2 lectures, some of you here already heard about that when I gave a talk in January 2011 at the university. So the general topic is the Monge, mass transport. Theory. So by the end of the first hour, I am going to outline what I am going to talk about. But let me start by formulating the Monge problem. And attached to the Monge problem, there is also a problem called Kantorovich problem. In the first hour, some of the definition, I will not insist on giving rigorous definition. Then later, I am going to talk about measure theory and so on, converse analysis, and there I will give more rigorous definition. So let us start with a very simple formulation of Monge problem. So Monge started with the following. He assumed that letter C of xy be the distance between x and y. So x and y are in Rd. And that is the square root of S1 minus Y1 squared plus SD minus YD squared. And C will represent C of xy is the cost for transporting a unit mass from x to y. Okay, and x is x1 to SD. Likewise, y is y1 to yd. Okay, so assume that I have a pile of dirt on one side, and I have an excavation on the other side. So the pile of dirt, let us look at a simplified case where it consists of, say, 4 points. This one has mass 1 over 4. That one has mass 1/2. This one has mass 1 over 8. And that one has mass 1 over 8. And if I add up the masses, I get 1. So assume we have some holes somewhere. And this first hole can support a mass 1/2, and that second hole can support a mass 1/2. So we are looking for a strategy to transport this whole pile of dirt to that holes. So these are holes. These are pile of dirt. So you may choose, for instance, to transport everything here, there. And I have filled this hole with 1/4. It looks like I don't have many other choices. I need to send this there and that there. And I am going to send that here. So that is a strategy. And so given this strategy, if I call this S1, S2, S3, S4, Y1, Y2, and if I call Mij, this is the mass transported from Si to Yj, then the total cost will be the sum over Ij, Mij, the distance between Si and Yj. So the strategy of transport is completely determined by the way I choose Mij. Mathematically, I can represent the pile of dirt, and I can represent the excavation by probability measure. So the pile of dirt will be mu naught equal to 1 over 4 delta S1 plus 1/2 delta S2 plus 1/8 delta S3 plus 1/8 delta S4. And the excavation will be 1/2 delta Y1 plus 1/2 delta Y2. Okay. So what you notice is the total mass here equal to the total mass there. So I call this mu1. And so I have two probability measures, mu1, mu naught of Rd is mu1 of Rd is 1. So in general, most problem will be given two arbitrary probability measure. So given mu naught, mu1, Borel probability measure. On Rd, and a map T from Rd to Rd, which is Borel, and the T will satisfy a mass conservation property such that if I look at this is the pile of dirt. That is the excavation. So you take any set here, B, and you look at the pre-image of B by T. And saying that T is a transport map is if you measure T inverse of B and you measure B, then this must be the same for all B in Rd Borel. Okay, so now let me compare what is here to what is there. Here I have chosen T from Rd to Rd, and there, in this example, you see that T of S1 So you see that I did not care about how to define T outside this set. But when you are outside this set, compared to this measure, you are on a set of 0 measure. And so this map T will be defined mu naught almost everywhere. And so what happened outside the support of the measure is not important. So by the end of this lecture, I'm going to define what is the support of a measure. When T satisfies this property, we call it a transport map. When you write C of x, T of x, mu naught dx, without mu naught, this is the cost you pay for transporting a unit mass from x to T of x. When I multiply by this, it corresponds to the cost I pay for transporting the mass mu naught ds from s to T of x. And I'm going to sum up over all the x. And summing up is computing an integral. So this is the cos mt, m for Monge. And so the problem is, can we find T star such that C of T star is smaller than C of T for all T, such that call this one satisfying the mass conservation condition. So that problem was first formulated by Monge when C is exactly that distance. And Monge conjecture that when the measure mu naught and mu 1 are absolutely continuous with respect to Lebesgue measure, there exists a minimizer for that. So, conjecture. This is Monge, 1781. Assume mu naught is absolutely continuous with respect to Lebesgue measure, and mu 1 is also absolutely continuous with respect to Lebesgue measure. So I am assuming that f naught is non-negative, f1 is non-negative, the integral of f naught is 1, the integral of f1 is 1, to satisfy the property that I have a probability measure. So assume this additional condition is not necessary, but when Monge was studying the problem, he studied that particular case. His conclusion is, then, there exists an optimal transport map. T star when C of xy is the distance between x and y. Any question? So let me comment on that result. When Monge formulated his problem, and he made some formal computation, it was very soon realized that this was a very important problem from the geometric point of view. And the National Academy of Science in France, they created a prize called the Boudin Prize, which will be awarded to the person who will solve that problem. And in 1887, Appel claimed to have solved Monge conjecture. And he got the Boudin Prize for that. Now, if you read through the work of Appel, you realize that this is not this is not a proof in the modern sense. So, in the modern time, it was realized that what was claimed by Appel cannot be considered as a proof. So, one needs to wait until 1972, where Sudakov solved the problem when d equal to 2 and left a gap when d is greater than or equal to 3. So, in fact, Sudakov also claimed that for any d, he has solved the problem. And it was later discovered by Ambrosio and few people that when d equal to greater than or equal to 3, there is a gap in Sudakov proof. And some of the argument he was using, they could find counterexample to these arguments. So in 1995, myself and Evans, we solved the proof for any arbitrary d, but we have to impose that the Lipschitz constant of F0 and the Lipschitz constant of F1 are finite. So we have to impose an additional regularity condition on F0 and F1, that they are Lipschitz function. So after that, there have been many work. I am going to cite only a few of them. One by Caffarelli, Feldman, Machen, some by Ambrosio, and some by De Pascali, and so on. So what these people did, they removed this condition and consider the case where F1, F0 are in L1 of Hardy. So let me comment on uniqueness. There is no uniqueness to be expected. Indeed, consider the following situation. I have -1, 0, 1, and 2. So I have some mass, 1/2 at -1, 1/2 at 0, and I have some mass 1/2 at 1 and 1/2 at 2. There are only two strategies So I call this S1, S2, Y1, Y2. The first strategy is T of X1 equal to Y1. T of S2 is Y2. The second strategy is T of S2 is Y1. T of S1 is Y2. So this strategy is going to generate the cos 1/2 S1 minus Y1 plus 1/2 S2 minus Y2. That one is going to generate the cos 1/2 S2 minus Y1 plus 1/2 S1 minus Y2. So S1 minus Y1 is 2. S2 minus Y2 is 2. And so what we have here is a total of 2. Now S2 minus Y1 is 1. S1 minus Y2 is 4. S1 minus Y2 is 1, 2, 3, is 3. And so the total is 2. And so every strategy here is optimal, and there is no uniqueness. So you can extend this to the case where F0 and F1 are absolutely continuous in the natural way. So I'm going to take this Dirac mass, I'm going to make it the uniform measure everywhere, and you will see that the translation will give you the translation where you transport. You have several ways of transporting this to that. You can just shift it, or what you can do is revert it, and you see that it gives you the same cos. So here is a difficulty with Monge problem. So the first one is the following. If I am given mu0 and mu1, it is not true that I can always find a T satisfying this property. So the set of, there may be no transport map transporting mu0 to mu1. You can see that easily by taking mu0 to be the Dirac mass at a point x, not mu1 to be 1/2 the Dirac mass at y1 plus 1/2 the Dirac mass at y2. There is no map which is going from S0 to y1, y2 onto. And so there is no transport map which is going to transport mu0 to mu1. Any question? You have a doubt? Transport. This one. Transport map. T star. Optimal. There is an optimal transport map T star when C of xy is the distance from S to y. So let me show the second and more serious obstruction. So there is this fact from this very strong result from probability theory. Assume that you have a space X, and you have on the space a measure. So assume that I have a space X and a measure mu naught with no atoms. So mu naught has no atom, meaning when I compute mu naught of a set consisting only on one point, I get 0. And assume you have Y with a measure mu1 such that mu1 of any set consisting of one point is 0. So mu naught has no atom, mu1 has no atom. Then there is this strong result from probability theory saying that if the spaces are separable, then there exists a map which is going to transport mu naught to mu1. This means that if we choose mu naught and mu1 appropriately, we are not facing this obstruction. And so it is not a serious obstruction. We just need to know how to choose mu naught and mu1. The most serious obstruction comes from the calculus of variation. So I am going to state a central result in the calculus of variation, and then we will check that it doesn't apply here. Central. So let S be a metric space. So in fact, all I need to take a topological space such that every compact set is closed. And being a house of topological space is enough. And let phi be a functional from x to negative infinity plus infinity, possibly taking the value plus infinity. And you want to know when does the problem infimum over S of phi has a minimizer. So the answer is a sufficient condition is answer. It suffices to have that the sublabel set phi less than lambda is compact for all lambda in R. So let us prove that property. Okay, so once you have such a result of the calculus of variation, when you have a specific problem to study, you are given. This is too strong. I am going to prove it in this case, but it is a too strong assumption. you are given a topological space, which is a outdoor space S. You are given a function. And you want to know if this problem has a minimizer. So you are going to look for the topology to put on S such that this property holds. So by starting with a metric space, I am imposing a topology. But usually what is done in the calculus of variation is you don't impose a topology at the beginning, but you choose a topology such that these label subsets are compact. It may happen that you cannot find any topology for which these label sets are compact. What people do often is assume that S is an LP space. Then often you choose the topology to be the weak topology. So let us prove this result. So claim 1. I claim that phi is lower semi-continuous. I claim that if Sn is in S converges to S infinity in S, then phi of S infinity is less than or equal to the lim f when n goes to infinity of psi of n. So if this level set is closed for every lambda, by definition you say that phi is lower semi-continuous. And one can show that phi is lower semi-continuous if and only if this property holds. So what I am doing now, I am proving only one direction. And the reverse direction is extremely easy. This direction is one which is more subtle. And notice here that in the proof, I assume that phi cannot take the value negative infinity. Otherwise, there is nothing to prove. This infimum is attained trivially. And you will see that if I am not in the trivial case, I am going to use the fact that phi cannot take the value negative infinity. So my proof will not work if I was taking the value infinity, negative infinity, and this case is a trivial case. So proof. Call this lambda. And assume without loss of generality that lambda is not plus infinity. Because if lambda is plus infinity, it means that phi is identically plus infinity, and there is nothing to do. Assume lambda is less than plus infinity. So I can take a sequence such that the lim f of phi of S n is the limit of a subsequence phi of Sn. Okay. So what the limit f does, it selects, you have a sequence, it selects the number in the sequences which give you the smallest value. And so this identity is always true for a subsequence. Pick any beta which is strictly greater than lambda. Okay. So I don't know that lambda can take the value negative infinity. And I want to exclude that case at the same time I am giving the proof. So since I don't know if we can take the value negative infinity, I take beta strictly greater than lambda. And so this assumption, I can make it whether or not lambda is negative infinity. By definition, if this limit is lambda, then we'll have phi of S and K is smaller than lambda than beta for K greater than a certain K naught. Okay? If the limit is lambda, it means that for K large, we are close to lambda, but beta being strictly greater than lambda, we are less than beta. Another way of writing this is S and K belong to the set where phi is less than beta. But this set is compact. And so if I take any sequence in a compact set, I can extract a subsequence which is convergent. And there I am using the fact that we have a Hausdorff space. So I'm going to subtract another subsequence, but I am not going to relabel it, since phi less than beta is compact. A subsequence of S and K. We don't relabel. Converges to some S infinity in the set where phi is less than beta. So let me write what this means. This means phi of S infinity is less than beta. So for every, now I can conclude the following. I can conclude that lambda cannot be negative infinity. Otherwise, I will have proven that phi of S infinity is less than beta for every beta greater than lambda. And so phi of S infinity must be negative infinity. But by assumption, phi can never achieve the value negative infinity. So I can conclude that hence lambda is not negative infinity. And negative infinity. Since it is not negative infinity, this proof I wrote, I said let beta be greater than lambda, then we have that conclusion. In particular, I can take beta, example, beta equal to lambda plus epsilon, where epsilon is arbitrary. So I'll have phi of S infinity is less than lambda plus epsilon for every epsilon. And so phi of S infinity is less than or equal to lambda. But lambda is, by definition, this lim f. And so we get what we want. Second claim. Claim 2. F of phi over S admits a minimizer. So for the proof, take a minimizing sequence. Call this I. Write I is the limit when n goes to plus infinity of phi of Sn. So I am using the elementary characterization of a minimizer, saying that if I have an infimum, if I have an infimum, then there exists a sequence. If I have an infimum of phi, then there exists a sequence Sn such that phi of Sn decreases to I. So this infimum is smaller than any value. So I pick an arbitrary S here. This infimum will be smaller than phi of S, and I call this lambda. For n large, actually, let me take this as I plus 1. Right, I is less than I plus 1. And assume without loss of generality that I is not plus infinity, because if I was plus infinity, phi will be identically plus infinity, and there is nothing to prove. Then I have Sn is a subset of phi less than I plus 1. This set is compact. This set is compact. I have a sequence in a compact set. Therefore, I can extract a subsequence which is convergent. This is compact. Hence, there exists Snk a subsequence of Sn converging to some S infinity in S. And so I am done. By claim 1, phi of S infinity is smaller than the limit f over k of phi of Snk. But this is a decreasing sequence. The limit of infinity equal to the limit of phi of Sn. This is I. Question? This is proof 1, proof of claim 1. Assume lambda. You're welcome. So phi of S infinity is smaller than or equal to the infimum. Therefore, S infinity minimizes phi. So in the calculus of variation in the 20th century, under the pioneer work of Charles Morey, people study a lot. Assume I am giving a functional, especially a functional of the integral form. I of u is the integral of f of u, or I of u is the integral of f of x, u, gradient of u, and so on. Under what condition on f can I say that this functional is lower semi-continuous? Because once I have a lower semi-continuity, this is a guarantee for existence of a minimizer. Now let us come back to Monge problem. So how is this normally done? Do I make a break, or I make 2 hours?
You break, or just choose to finish it before, a little bit early, like you choose.
Okay.
What's better?
Okay, so I will make a break at 11, and then for 5-minute break. So let us come back to Monge problem. Obstruction, second obstruction. In Monge, in solving Monge problem. So here is the data. Mu0, mu1 are 2 probability measures on RD. And C of xy is the distance between S and y. So gamma is the set of t, call it tau. This is the set of t from RD to RD, such that the mass conservation property is satisfied. T pushes mu0 forward to mu1. So let me say what is the meaning of this. By definition, if I have a set x, and I have a set y, and I have a measure mu0 here, and I have a map t going from S to y, I can use the measure and the map to define another measure here. It is called the push forward. By definition, the push forward of t, mu0 by t, if I apply to a b, take b here, and I want to measure b, this is mu0 of t inverse of b. And so you can see that this condition, t pushes mu0 forward to mu1, is equivalent to this equal to mu1 of b for every b Borel. So the push forward of mu naught, if I apply to B, this is mu naught of T inverse of B for B in RD. The functional to minimize it is Cm of T is the integral over Rd of the norm of x minus T of x mu naught of x dx. And no one knows of any topology such that Cm of T is less than lambda. No one. Of a topology such that this is compact in tau. Okay, so maybe the best way to write it is the set of T in tau such that Cm of T is less than lambda is compact for all lambda real number. For instance, if you take the weaker topology in assume that mu naught and mu 1 are, say, of compact support, and take the weak star topology in L infinity. Then this sub-level set is weakly compact. But if you take the bigger set of L infinity function, however, if you restrict yourself to the set of tau, you don't anymore have the weak compactness property. Because if you take a sequence which satisfies this property, and the sequence Tn converges weakly to T, this relation is not linear in T. And so you don't know that the limit will satisfy that property. So weak convergence means that when you integrate against so Tn converges to T in L infinity star, mean that the integral of L Tn converges to the integral of Lt for every L, which is continuous, for instance. And this is not enough to tell you that at the limit T will satisfy that property. So in 1942, Kantorovich came with a problem. He turned this set into a bigger set by the following way.
Said that this T are Borelian satisfying that condition, just that.
Yes. So you are distinguished between Borelian and measurable. Is that the issue?
No, I'm just asking.
Yes. Yes, the set of Borelian functions satisfying this property.
Yeah, but since you have because the measurable, you would have to specify the measure. I don't know. Mu0.
Yes. So I should have said that anytime I'm dealing with a measure, I am dealing with a Borel measure. So I should have said mu0, mu1 are Borel measure. I consider T, which are Borel measure. So in that case, if you take a T, which is mu0 measurable, then you modify it on a set of zero measure, and then you get a Borel function. And so there is no distinction if I impose Borel or if I impose measurable with respect to mu0. Okay. So let me tell this story, which is interesting about mathematics, pure mathematics, and abstract mathematics. So Monge formulates his problem for C of xy equal to the norm of x minus y, and for T, Borel map from RD to RD. So Kantorovich, this is Monge. Kantorovich came and said C of xy arbitrary. And that T is a multi-valued Okay, so 2 to the power RD is the subset of the set of RD. So Kantorovich came with that problem. The fact that he looked at multi-valued map looked reasonable. Okay. Now, the fact that he looked C arbitrary, one may wonder first what is the motivation why he will do that. And then several people, Brunier, C of xy equal to x minus y squared. And the T from RD to RD. Okay. So one may think he's not attacking the real problem. Why he's not studying the Monge problem? He introduced a cost function claiming that Kantorovich said you can take any cost function. In particular, you can take this one. Why isn't he taking the Monge cost? So it turned out that solving this was instrumental understanding that. So after this is solved, we start to understand why this is difficult. We start to understand what went through in the proof here, but didn't go through there. And so we start thinking in what direction one should look for if one would like to solve the problem. Okay. So this is to just say that it is not necessarily because you don't have yet a motivation for what you are doing that it doesn't make sense to do it, because eventually you may get your idea from, for solving the big problem, you may get it from solving a simplified problem. So with Brunier, we'll realize that I could replace this by any strictly convex function. And the main difficulty here is this one is not a strictly convex. Here, with strictly convexity, you have uniqueness. So it is well known in many fields. When you are looking for a solution to something, if you don't have uniqueness, it is a hard problem. If you have a uniqueness, it tells you that if there is a method which can do it and suggests some solution, then this is your solution. If you don't have a uniqueness, you don't really know how to look for your solution. So I am going to stop here, and in, say, 5 minutes, I will, let's say 10 minutes. It is, I'll say 11:15. 11:15. I will start with Kantorovich problem. Yes.